hit record on this. I don't know, it's just a test, Dylan. We're just testing it. The set of all points that make the equation true is called the graph of that equation. So what we're going to do is we're just going to graph some stuff. Hopefully, this is going to be like... Oh my gosh, we're graphing linear equations today, right? There is some tricky stuff. This is a linear equation, so I hope that you know how to graph that because you've been doing that for a very long time. If you don't know how to graph it, an XY chart always works, but hopefully. I'm only doing one of these, but it makes you feel better about this. When we graph, we start with our y-intercept, which is -1. That's B. And then M is our slope, rise over run, right? So we can say up to over 1, up to over 1. And we connect it, and we put arrows on it to show that it keeps going forever, and that there are an infinite amount of points that make that true. Yes? What if I asked you to graph x squared minus 3? What kind of graph is that? Yeah, a quadratic, a parabola, a U-shaped graph. Again, if you're not sure what it's going to look like, you can always make an XY chart. Pick some points. If you know the shape of it, it makes things easy. On the next slide, I kind of did a little review of parabolas if you forget. Marsu? Where is Megan? She was here. So she came for... Why is she going to Pennsylvania? Why wouldn't she tell me she's going to Pennsylvania?
She probably assumes that you...
For the rest of the week?
Yeah.
I think it's...
But she can't do powder puff. She's upset.
If I picked 0 for x, what would I give for y? -3. If I picked 1 for x, what would I get for y? 1 minus 3 is -2. If I picked -1 for x, what would I get for y? Oh, -2 again, because -1 squared is still +1. And the shape is a parabola. Hopefully, you know that normally x squared starts at 0, 0, and if you remember anything about transformations, what does it mean when you add or subtract a number outside of that x squared? It's a vertical shift. So if you remember those things about transformations, you don't have to make XY charts, because you can just say, oh, that's just taking x squared and moving it down 3, and it's the same shape. And so that's really a nice thing to know as you're graphing these. So I just made a little slide here reminding you about quadratics. Okay, I gotta erase all this first. Very sadly. I couldn't try this out at home because I don't have software.
Use your entire form.
So quadratics, they're not getting that complicated right now. We will look at a couple other ones tomorrow. But most of them are like y equals ax squared. So remember that if you graph that, if there's nothing added or subtracted, it's just going to start at 0, 0. If there's a number in front of x squared, do you remember what that does to the graph? Stretches it out, shrinks it like that. We should know it makes a parabola. The vertex is that turning point on the graph, right? If it opens up, that's a minimum. If it opens down, it's a maximum. So I'm going to put it's the max or min of the graph. It's just me hitting enter, and it automatically put a little dash there. symmetry. What's the axis of symmetry in a parabola? The line that cuts down the center, that cuts it in half, that you could fold it over. If it's centered at the origin, the axis of symmetry is just the y-axis. But it's always x equals whatever the x coordinate of the vertex is. So x equals, I don't know what to say. I was going to say x equals 0 or y equals ax squared. But if it's moved over, right, it's going to be a difference. And hopefully you know that if there is a positive number in front, that's how you know it opens up. And if there's a negative number, it flips over the y-axis, the x-axis, and it opens down. Again, something you've been doing since algebra 1, right? Is that right?
Yeah.
All right, what about intercepts? What does it mean to be an intercept of a graph? Either one, right? What's x-intercept? This fanciness. I haven't read anything. How do you find an x-intercept where it crosses the x-axis? Solve what? What do we know about every point on the x-axis? This kind of goes back to that distance thing that we did. What's this point? This is the point 0, 0. This would be the point like 4, 0. This would be the point like -3, 0. Y always equals 0. So normally you think solve the equation because you just set it equal to 0 because if it's equal to y, you're just making y equal to 0. So all you have to do to find the x-intercept is make y equals 0 and solve that equation, right? So make y equals 0 and solve. What you guys were talking about on the Padlet, find the solutions where you were saying it's the x-intercept, you said it equals 0, you're finding the x-intercepts. We don't usually call them x-intercepts because we call them zeros or solutions, but they're really just x-intercepts of the graph. Besides linear equations, we don't really talk a lot about y-intercepts, but every graph could have a y-intercept, if it touches it or not. And again, the definition is going to just be where it crosses the y-axis, and every point on the y-axis is going to have an x-coordinate of 0. So all you have to do to find a y-intercept is make x equals 0 and solve. So there are some questions on your homework today that they give you a bunch of different equations, some linear, some quadratic, but some other ones, like some square roots, some sideways parabolas, which is probably something that you haven't done before, if you haven't taken pre-calculus, finding the x and y intercepts. And so you just need to know to set them equal to 0. Questions about that? Let's do a couple examples. So we'll start with a quadratic. Find the intercepts and sketch the graph of the function. You could put homecoming on the second. You could put fall festival on the third, but that's really fun for you. But you could put homecoming, that would be nice. So if I'm going to find the intercepts, all you do is make one equal to 0 and solve for the other one, right? So if I make y equals 0, I can just add 4, and what would my x-intercepts be? Yeah, don't forget when you take the square root of both sides that you get plus or minus 2. And I'm okay for finding intercepts. I'm okay with you writing it like that, or if you prefer, you could actually write them as ordered pairs. If you were going to graph that, it would cross at both 2 and -2 on the x-axis. Chase here. You're not allowed to sleep. That's your only warning. Next time you're going to ISS. And so you look pretty tired, so you might want to sit up so you don't go fall back asleep. If I find the y-intercept, I just make x equal to 0, which is just y equals -4. Another good use of intercepts is we have 3 points to our graph now. Like, that's probably plenty of points to make this graph, right? How many problems do you think I gave you on your homework to graph? I think 6. That's not so bad, right? I'll even give you graph paper if you want. So we could graph this knowing what we know, just like we graphed the last one. But graphing with intercepts is a great thing because I know it crosses at -2 and +2 on the x-axis. And if you wanted to write this one as an ordered pair, that would be at 0, -4. So I get something like that. What if I gave you this one, though? Oh. Definitely can still find the x-intercept and the y-intercept, and then we can see what it looks like, right? So if I'm going to find the x-intercepts, I'm just going to make y equal 0. Which means I get just 0, right? And the y-intercepts would be 0 equals 2y squared. Oh, dang. It's just the same thing, right? 0 equals y squared. 0 equals y. Plus or minus 0 is just still 0. Which means we really only got 1 point, right? The x-intercept and the y-intercept are the same point. It's the origin. Which means that if we're going to graph this, we're going to maybe want to pick some other points to go along with it. Here's what I want to show you that's different about this equation. Normally, we like to solve for y because then we can pick our x's and we can plug them in and find y. On this one, if we wanted to solve this for y, it's going to get a little ugly. You could do it. If you wanted to solve this for y, we could divide by x, and I'd get x divided by 2 equals y squared. Then what do I have to do? Square root both sides, and when you square root both sides of an equation, you would get that y equals plus or minus the square root of x over 2. That does not seem like that much fun. Which means you don't have to do this to graph it, all right? You can graph it in this form, but instead of picking x's first and plugging them in for y, do you agree that in this case it's going to be easier to pick y values and plug them in to get the x values? So it's almost kind of like the independent and dependent variable have changed for us when y is squared as opposed to x. So we already know 0, 0 works. But now I'm going to pick y values to get x values. So what's a y value I can pick? 1 sounds like a good y value. And if I plug 1 in for y, what's the x value I'm going to get? Just 2. 2 times 1 squared is 2. And let's just pick 2. If I plugged 2 in for y, what would I get for x? 8, right? 4 times 2 is 8. What if I picked -1 for y? I also get 2. So to me, it seems kind of just like the parabola. Like over here, if I plugged in negative for x's, I get the same thing. Only now I'm picking different numbers for y, same numbers for x here. So look what happens when I graph these numbers that I have. Oh, the black doesn't work very well on the ball. So 0, 0, 2, 1, 8, 2, 2, -1, and we could say if we picked -2, we would also get 8. Sorry, if we picked negative, yeah, we would get -8. Which means, some of you are already picking up on it, if we connected these, we're going to get a parabola turned on its side. And that's always true. Oh, what happened to my stuff? I want to go back. The writing up there, the equations. I hate Google Slides. When x is squared and y isn't, like, we recognize that's a quadratic. We've been doing that since algebra 1, always. But it's a quadratic that opens up or down. It's a function. It passes the vertical line test. When y is squared and x isn't, that's going to be a parabola on its side, which means it's going to open left or right. Same rules apply. If the y squared was negative, then it's going to open backwards. It is not a function. It does not pass the vertical line test. That's why if you try to solve it for y, you get plus or minus a radical. Do you remember in algebra 2 graphing radical functions that were like half of a parabola on its side? Like if you graph y equals the square root of x, when you graph that, it kind of looks like this. Well, that's because you're only graphing half of a parabola on its side. If you put the plus or minus there, you get the whole parabola on its side. So when you see y squared and x isn't, it's kind of giving you both the positive half of the radical and the negative half. So you get a parabola on its side. And so once you know that, it's easy to recognize. It's just like a parabola that opens up and down. It's just opening side to side here. Okay? You could have it also an axis of symmetry. Its axis of symmetry is going to be the x-axis or some horizontal line if it was moved around. So that's kind of something new. In pre-calculus, we talked about those when we did conic sections, but I don't think you did that in algebra 2. So that's kind of a new graph, and there's a couple of those on there. Okay, the other thing we need to talk about before I can be quiet today is symmetry. How can we talk about symmetry with graphs? Why do we talk about with symmetry with graphs? We talk about it because if you know symmetry, it helps you, right? This graph is symmetric about the y-axis, because you could take that and fold it over. This graph is symmetric about the x-axis, and the rules really make sense if you just think about if it's symmetric, what stays the same and what changes. So I have a lovely picture for you that I Googled and found for you. A picture about symmetry.
Inappropriate?
No, is it math?
But you said you found a lot of
There's a great, oh, look at this lovely symmetry. I say like just do one at a time. I need a screen shade, but there's no screen shade. In your book, there's a really great picture. You should look at your book sometimes. I feel like you don't. I feel like I'm not preparing you for the real life of college because you have to read your book. Hopefully, you're all going to get this credit, and you don't have to take math in college, right? And you won't have to learn to read your math book. On page 134, I actually like the one in your book better than the one I found on Google. But there's a great graph or a great picture that talks about symmetry. What does it mean to be symmetric in words? How to do it, and then an example of an equation that we know or that we should know that's symmetric. Basically, it's just all about what changes and what doesn't change. So the red graph is the original graph. So if you had this graph and you wanted it to be symmetric about the y-axis, it just means you'd flip it over. So notice that the y value stays the same, but the x value is negative. So I always say for y-axis symmetry, it means that if xy is on the graph, then negative xy is on the graph. Which basically means x squared, right? A good example of that, if you have x squared, when you plug in a negative x, it's not going to change the y value. You're still going to get the same y value out. So any kind of like even exponent is going to give you that. I'm going to skip origin symmetry for a minute, but x-axis symmetry is like the sideways parabola that we just talked about. So if you had this red graph and you wanted to flip it over the x-axis, now the x's are going to stay the same, but the y is going to change sign. So for x-axis symmetry, I say if xy is on the graph, then so is x negative y. A good example of that is x equals y squared. Because if y is squared, then both y and negative y give you the same x value. So that's an example of x-axis symmetry. If something is symmetric with the x-axis, it's not a function, right? It's going to fail the vertical line test. So we don't see a lot of that in Algebra 2 because we like functions. Circles, right? A circle would be an example of, well, depending on where it was located, but it would not be a function. And then we have this origin symmetry. Origin symmetry is when both x and y change sign. So again, think about if you had this red graph and you flipped it down. I always think about going from this quadrant to this quadrant. I think it was someone last year made a really good observation. It's basically like you flip it in the x-axis and the y-axis. So like if you took this and you flipped it over this way and then you flipped it that way, or you flipped it over the y first and then over the x, and I'd never thought of origin symmetry that way, but it made a lot of sense. So both the x and the y change signs. So xy goes to negative x, negative y. What's a good example of that? Well, function-wise, y equals x cubed is an example of origin symmetry because y equals x cubed looks like this. So like it goes up and then it's negative going down. A circle centered around the origin, a circle centered around this, right? It's going to be symmetric. That's a bad circle. But it would be symmetric about all of them if it was centered at the origin because you could flip it down and over and that way. So graphs can be symmetric with 1, 2, all of these or none of these depending on the graph, right? Like what if I gave you this graph? Right? That graph isn't symmetric with the x-axis, the y-axis, or the origin, but some graphs, like a circle, are symmetric with all three, and we're going to talk about circles tomorrow. So maybe we should test for symmetry on the ones we just did, even though we looked at the graph. It's easy if you look at the graph. It's harder if I just give you an equation. And I'm using the same equations we just did, so we already know the answer. I just want to show you how you can use the test for symmetry to do those. So this is the same. I think I didn't even renumber them, right? Is number 4 from number 4? You already have a number 4? In your book, they say, use tests for symmetry, which means that they want you showing that you're using this whole idea of the x or y changing signs. In pre-calculus, when I give a test over this, we already have a test over symmetry, I make them show me some work if they want to get partial credit. If you're right and you don't show work, I'm going to count it right. Well, unless the Ivy test says something different. But for me, if you can look at it and know, I'm okay with that. But if you get it wrong and you don't show me the process, I can't give you partial credit. So that's kind of the downside of that. But what you're supposed to do is you're supposed to say, well, if I was going to test for x-axis symmetry, x-axis is when the y changes but the x doesn't. So that means that if I plugged in a negative y in here, it shouldn't change the equation. I should get back what I started with. And it's really easy to tell that without showing work, but I'm going to show a little work on this one. So all I'm going to do is I'm going to leave x the same, and I'm going to replace it with negative y. And very easily you can see this does not match the original equation, so that means it is not symmetric with the x-axis. No. The y-axis, did I mention how much I hate this? Whatever. Go back. Okay. Y-axis means that for every xy, negative xy is on the graph. And for me, automatically I can see that when I plug in negative x in there, right, negative x squared is positive x squared because a negative times an x, a negative times a negative is a positive. So since this is the same as what I started with, I can say that this is symmetric about the y-axis. And then the origin, if you plug in two negatives, is it going to be the same And the answer to this is going to be no, because you're going to get, for the origin, if you plug in negative x, negative y, that is not the same. So this one is only symmetric with the y-axis. The purpose of this is when we graph really crazy stuff, that this could help you know if it's symmetric, then I know that for every x I get, I'm going to have the same thing down there. So if you notice on your homework, if I gave you x equals 3y squared, you should know, oh, the y is squared, so that means it's going to be symmetric in the x-axis, so you would know that every value you got up here is going to reflect down there. That's kind of what they're hoping that you do. So I gave you 6 problems on your homework to graph, and then I want you to go back and tell me the symmetry for those 6 problems. Oh my gosh. So here you go. Page 138, 139. I want you to do 3 through 18, multiples of 3. Those are all graphing. Some are just linear, some are quadratic, some are the parabolas on their side. I even threw in maybe a cubic in there and a square root in there. Make an XY chart if you don't remember what they look like. And then I wanted to give you 21 or 22, which says go back and tell the symmetry, but it says tell the symmetry for all 20 problems. That's kind of a bit much, right? So instead of that, underneath each problem, 3 through 18, if you could just also do the symmetry. It also says label x and y intercepts, so you could find them by splitting in zeros, or you could just graph them and find them that way as well. So it's like 6 problems, but really it's like doing 3 things, right? Graph, x and y intercepts, symmetry. I know, isn't that funny? We did 3.1 on our last test. 3.1 was midpoint distance. I have graph paper if you want graph paper. Does anybody want graph paper? Oh, that was so close.
I think whenever you ended up, you did not have
just left the thing on his desk.
I was so close. What, anybody want that graph paper I threw on the floor? Anybody want this graph paper I threw? This is nice graph paper. The hard part about graph paper, if you normally keep your homework all in the notebook, and I keep track of this for the unit, right? Tomorrow we're going to look at graphing maybe some more complex quadratics and absolute value in circles and semicircles. I know, it's so, it makes it a function, so you just do half the circle. And that will help you in calculus, because we do those in calculus. And everyone's always freaked out about it, that it's a semicircle. Semi, I never know what to say.